This is a video for AQA Discrete Mathematics, Graphs and Networks, section 4.2, where we're looking at Kuratowski's theorem. Kuratowski's theorem, produced by the Polish mathematician Kuratowski, can be used to prove that a graph is non-planar. The actual proof of the graph is quite complex. However, its result is quite intuitive and uses the idea that K5 and K33, graphs that we've already come across, are non-planar. But as well as that, we have to be able to understand the idea of a subdivision of a graph. So if we consider this, which is K4, and we know that K4 is planar, then a subdivision takes an edge. For example, we could take the edge DC and replaces that by two edges with a new vertex in between. So we now got the edges DE and EC. Essentially, that's the same as, we might think is the same as putting a node in the edge DC. But really what we're doing is replacing that one edge by two new edges. And of course we can do that over again. So there's what we have now, but I could, for example, do that and put two new nodes. So here I've done it twice, and so now we've got F and G. So instead of the edge DB, I've now got edges DF, FG and GB. So each time we do that, we get what is called a subdivision of the original graph. Now, as the original graph was planar, it's quite clear to see that any subdivision of that must be planar. So we say that the subdivision preserves planarity. Kuratowski's theorem says that if a graph has a subgraph, in other words part of it, which is K5 or K33, then the graph itself must be non-planar. Now that's clearly quite intuitive because we know that K5 and K33 are both non-planar, so that if we can find those inside a graph or as part of a graph, then the graph itself must be non-planar. But what is quite interesting, or very interesting, about Kuratowski's theorem, it also says the opposite of that in a way. It says that if a graph does not contain either K5 or K33, it is therefore planar. So therefore, looking for these subgraphs is the key to Kuratowski's theorem. If we can find them, then the graph itself is not planar. And if they aren't there, then the graph must be planar. So what we're looking for is these patterns. We're either looking for a pentagon star formation, which would give us K5, where each of the 5 nodes is of order 4, or where we've got 6 nodes where they're connected in this fashion, and perhaps looking for this pattern, which is the cyclic formation, where each of the nodes is order 3. Now these can be quite difficult to spot, so it does take a little bit of practice. Here's two quite straightforward examples. In the first one, we can see that if we ignored F, then what we're left with is K5. So K5, being a subgraph of the graph G, means that this is non-planar. Also, we can see that in the second diagram we've got a subdivision. So again, ignoring F, then from A to E, that would give us our graph which is a subdivision of K5. Let's try applying Kuratowski's theorem to these two to decide if either of them is planar. If we look at the one on the left, you can see that it's probably got K33 in there, so we just need to check that. And indeed, if you take out AB and DF, you can see that we are indeed left with K33, and therefore this is non-planar. So moving across to the right, again it looks like it might have K33 in there, but if we check C, this is order 2, so therefore it's not possible that it's K33. So then we need to check for K5. Well, if K5, we'd have to have 5 nodes of order 4, and we can see that E and A are order 3, so E and A are order 3, and therefore it's not K5, or K5 is not contained in that. So if we haven't got K33 or K5 contained in the graph, therefore it must be planar. In this question we're asked to use Kuratowski's theorem to show that this graph is not planar. Well, firstly, if we rule out the edge going from F to C, you can see that then F itself is order 2. And then if you look at what we're left with, A, E, D, C, B, that would be equal to K5. So what we have by removing FC is a subdivision of K5. So we can say that because G contains a subdivision of K5, then this must be non-planar. In summary then, Kuratowski's theorem says that if a graph contains a subgraph that is a subdivision of either K5 or K33, then it cannot be planar. If it doesn't contain a subgraph of that nature, then it must be planar. So the key to this is looking for these patterns, either the K5 signature one, which is 5 nodes of order 4, or K33, the 6 nodes of order 3. If you can find either of those, you must have a non-planar graph. If you can't find them, then the graph is planar. Now that completes this video, and in the next one we'll be looking at the idea of isomorphisms.